Tonight, we drift into the currents of time itself, exploring the profound and wondrous tapestry woven by one of humanity's most persistent dreams, the journey through the fourth dimension. Our exploration begins, as so many have, in the quiet contemplation of a master storyteller, H.G. Wells, who first gave this dream a tangible, mechanical form. Let his words be the vessel that carries us from the familiar shore of the present into the deep, mysterious ocean of what was and what might be. Imagine, if you will, a dimly lit Victorian laboratory. The air is thick with the scent of ozone and machine oil, the faint, metallic tang of creation. Shelves are laden with glass beakers, coiled wires, and leather-bound books filled with equations that challenge the very foundations of reality. And at the center of it all, a strange and beautiful contraption of nickel, ivory, and shimmering crystalline quartz. This is the stage upon which our traveler, a man of science and profound curiosity, prepares to embark on the ultimate voyage. Feel the quiet anticipation in the room, the weight of the moment, as he makes his final preparations. His voice, a whisper from the past, reaches us now, filled with a sense of awe and trepidation. It was at 10 o'clock today that the first of all time machines began its career. I gave it a last tap, tried all the screws again, put one more drop of oil on the quartz rod, and sat myself in the saddle. I suppose a suicide who holds a pistol to his skull feels much the same wonder at what will come next as I felt then. I took the starting lever in one hand and the stopping one in the other, pressed the first, and almost immediately the second. I seemed to reel. I felt a nightmare sensation of falling, and looking round, I saw the laboratory exactly as before. Had anything happened? For a moment, I suspected that my intellect had tricked me. Then I noted the clock. A moment before, as it seemed, it had stood at a minute or so past 10. Now it was nearly 3:30. In that single, breathtaking moment, the familiar, comforting linearity of existence was shattered. 5 hours vanished into the ether, consumed by a journey that lasted but an instant for the traveler. It is a profound disorientation, a vertigo of the soul. The world, which had always marched forward at a steady, predictable pace, was suddenly revealed to be a far more malleable, more mysterious thing. The clock on the wall, once an arbiter of absolute truth, became merely a local reference point in a vast, unseen river. The traveler, emboldened by this first taste of temporal manipulation, grips the controls with a newfound resolve. The initial tremor of fear gives way to the irresistible pull of discovery. He is no longer just an inventor. He is an explorer on the verge of a new continent of experience. The laboratory, his sanctuary of logic and reason, is about to become a flickering ghost. I drew a breath, set my teeth, gripped the starting lever with both hands, and went off with a thud. The laboratory got hazy and went dark. Mrs. Watchett came in and walked, apparently without seeing me, towards the garden door. I suppose it took her a minute or so to traverse the place, but to me she seemed to shoot across the room like a rocket. I pressed the lever over to its extreme position. The night came like the turning out of a lamp, and in another moment came tomorrow. The laboratory grew faint and hazy, then fainter and ever fainter. Tomorrow night came black. Then, day again, night again, day again, faster and faster still. Then, in the intermittent darknesses, I saw the moon spinning swiftly through her quarters from new to full, and had a faint glimpse of the circling stars. Here, we witnessed the very fabric of reality begin to fray from the traveler's perspective. The steady rhythm of life accelerates into a frantic, blurred cascade. His housekeeper, Mrs. Watchett, moving at her normal, human pace, becomes a projectile, her life's moments compressed into a single, fleeting streak of motion. This is the heart of relativity, imagined decades before Einstein would give it a mathematical voice. Time is not a universal constant. It is a personal experience, a local phenomenon. For Mrs. Watchett, in her world, time flows as it always has. But for the traveler cocooned in his machine, her time is a raging torrent. The world outside speeds up, its days and nights flicking past like frames in a zoetrope. The celestial clockwork of the cosmos, the patient dance of the moon and stars, becomes a dizzying celestial ballet. He is an island of stillness in a hurricane of moments, a silent witness to the frantic rush of the world's future. And in this dizzying acceleration, a new, more terrifying thought begins to crystallize in his mind, the problem of stopping, the problem of re-entry into the stream of time. And so my mind came round to the business of stopping. The peculiar risk lay in the possibility of my finding some substance in the space which I, or the machine, occupied, jamming of myself, molecule by molecule, into whatever lay in my way. This is the first, most practical, and perhaps most terrifying conundrum of time travel. The traveler understands that he is not just moving through time, but through space-time. And the space he occupies now, this very moment, will be occupied by something else in the next. To stop, to rematerialize, is to risk a catastrophic intersection with solid matter. His very atoms, his essence, could be forced to coexist in the same infinitesimal space as the atoms of a wall, a piece of furniture, or even the air itself. It is a vision of disintegration, of being unmade, at the most fundamental level. This initial fear, this concern for physical displacement, is but the first ripple in a vast ocean of paradoxes. For the true challenges of time travel extend far beyond the walls of a single laboratory. They are written into the very laws of the cosmos. Let us contemplate this for a moment. If a time traveler, sitting comfortably in his machine on the surface of our Earth, were to journey just one single day into the past, or one single day into the future, a profound and lethal surprise would await him. Unless his machine was also a fully equipped spacecraft, complete with a robust life support system and a pressurized capsule, his journey would end in a matter of minutes. He would find himself not in his laboratory, but in the cold, silent, unforgiving vacuum of outer space, irradiated and gasping for a breath that would never come, a lonely, abandoned ghost in the cosmic wilderness. The reason for this stark reality is one of celestial mechanics, a grand and silent dance that we are all a part of, every moment of our lives. Our planet, Earth, is not a static stage. It is a dynamic vessel, hurtling through the cosmos on a journey of unimaginable speed and scale. As it pirouettes on its axis, giving us our day and night, it is also engaged in a grand orbit around our Sun. This solar orbital speed is a staggering 108,000 kilometers per hour, or roughly 70,000 miles per hour, but the journey does not end there. Our entire solar system, a family of planets, moons, and asteroids tethered to our star, is itself a passenger on an even grander voyage. It circles the dense gravitational heart of our Milky Way galaxy at a speed of 720,000 kilometers per hour, or 450,000 miles per hour. We are all moving, all the time, at speeds that defy our everyday comprehension. So picture our time traveler, sitting in his machine in Los Angeles or London or Beijing. He sets his controls for just 24 hours into the future and engages the mechanism. The world blurs, the clock spins, and he arrives. But the Earth he left is no longer there. In those 24 hours, the Earth, in its relentless orbital path, has traveled millions of miles through the cosmos. The traveler would materialize in the empty space that Earth occupied a day before, a vast, cold, and utterly hostile void. If he journeyed to the future, he would find himself millions of miles behind the planet, watching it recede into the distance. If he journeyed into the past, he would materialize in front of the onrushing Earth, with likely catastrophic results. Without a space capsule, without life support, the traveler would be reduced to a lifeless, frozen corpse in the blink of an eye, a tragic monument to a miscalculation of cosmic proportions. Even if our intrepid voyager were to survive this initial peril, safely ensconced within a sophisticated time-space ship, a host of other dangers and paradoxes lie in wait, like hidden currents in the river of time. There is the very real prospect of premature aging, or its opposite, a kind of temporal stasis we might call the Rip Van Winkle effect, where the traveler remains young while the world outside grows old. The journey itself, the acceleration required to manipulate time, would subject the body to life-threatening G-forces, crushing pressures that could turn bone to dust. And for those who dare to seek the past, the physics becomes even more bizarre, more counterintuitive. To travel backward in time, to exceed the cosmic speed limit of light, may necessitate a fundamental transformation of matter itself, a shift into a state of negative energy and negative mass, a miniaturization into the quantum foam. And perhaps most profoundly, the very act of traveling through time would alter the destination. Each moment of space-time is not a solid, immutable block, but a delicate, probabilistic quantum weave. As one journeys through it, one interacts with it, leaving a wake, a ripple of change. You may travel to a past or a future, but perhaps never the past or the future you intended to find. This is a subtle and deep concept, rooted in the strange and wonderful world of quantum mechanics, particularly the Copenhagen and many worlds interpretations. These frameworks, developed by brilliant minds like Niels Bohr, Werner Heisenberg, and Hugh Everett, suggest that reality at its most fundamental level is not fixed until it is observed. The very act of looking changes what is seen. So, if a time traveler journeys 100 years into the future, their passage through each intervening moment, each quantum instant, would subtly affect and alter the composition of that moment. The future they arrive in is, by definition, a future that has been changed by their journey to it. It is a new branch on the tree of possibility. If, somehow, the future was not altered by this journey, it would imply a paradox of predestination. It would mean that this future already existed, perfectly formed and immutable, and that the traveler's journey to it was always a part of that future's history. His arrival was not a new event, but an echo of an event that had, in that timeline, already occurred. The very tenets of quantum mechanics suggest a more fluid, more mutable reality, an endless assembly of infinite possible futures, some of which may be altered by our choices and our journeys, and some which may remain untouched, existing in a tranquil state of probability until they are visited. The same logic applies, in reverse, to a journey into the past. Imagine a traveler from the year 2050 setting a course for 1950. As their machine moves backward through the temporal stream, it interacts with every local moment of that entire 100-year span. The quantum fabric of each instant is touched, disturbed, and subtly altered by this passage. The past they seek to visit is reshaped by the very act of traveling to it. The past becomes a past. It is no longer the pristine historical record, but a new version, a new timeline, colored by the traveler's presence. If that past, and every moment leading back to it, were somehow not altered, it could only mean one thing. The journey was always meant to happen. It was part of the established record of that past. In essence, the traveler must have already journeyed to the past before he ever decided to journey to it. His departure in 2050 was not a choice, but the fulfillment of a causal loop that was already closed. Let us follow this thread a little further into the labyrinth of paradox. Our traveler arrives in 1950 and decides to stay. The past, for him, has now become the present. He lives his life, day by day, year by year. The world progresses. Time flows forward. He watches as the world moves through the decades, towards the year of his own birth. He sees himself born into this new timeline. He continues to age, as this new present marches inexorably towards the year 2050, the very year he originally departed from. On that fateful day, in this new timeline, what happens? Does he watch his younger self, the self that grew up in this altered past, step into a time machine and depart for 1950? If so, he will then be there to greet himself upon his own arrival, creating a stable, self-consistent loop. He leaves, he arrives, he lives, he watches himself leave, and the cycle repeats. But consider the quantum implications. Each journey could create a new branch, a new many-world. What if each time he departs in 2050, he arrives in a slightly different 1950? An infinite number of time travelers, all versions of the same man, could arrive simultaneously in Ota, past, or perhaps in an infinite array of separate, subtly altered pasts, each a unique thread in the cosmic tapestry. The single river of time splinters into an endless delta of possibilities. This is because time, as the great Albert Einstein revealed, is not a universal metronome, ticking at the same rate for everyone, everywhere. Time is relative to the observer. It is a personal experience, and since there are innumerable observers in the cosmos, from the smallest microbe to the largest galactic supercluster, there can be no single, universal, past, present, or future. There are only infinite, overlapping, and constantly shifting perspectives, all in motion. There is more than one present, because time itself is not uniform. It is affected by gravity, by acceleration, by your very frame of reference. Time slows down in strong gravitational fields. It slows down as you approach the speed of light. Think of it like the weather. The weather in Beijing is different from the weather in Berlin. So too is the experience of time. The greater the distance between two locations in the cosmos, the greater the potential difference in their temporal flow. This is because time is inextricably linked to space. They are two sides of the same coin, a four-dimensional fabric that Einstein called space-time. And this fabric is not static. It is in constant, dynamic motion. The past in a distant galaxy may, from our perspective, overlap with our present here on Earth. The present moment happening right now in the Andromeda Galaxy will not be observable on Earth until some 2.5 million years in our future, when the light from that event finally completes its long journey to our eyes. According to Einstein's revolutionary theorems of relativity, the past, the present, and the future are not a neat, linear progression. They overlap. They exist simultaneously, but in different distant locations within the grand architecture of space-time. This led Einstein to a profound and almost mystical conclusion. In a letter to the family of a deceased friend, he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion. This is not merely poetry. It is a conclusion drawn from the deepest laws of physics as he understood them. The strange world of quantum physics, with its uncertainty principle, its many worlds, and what Einstein himself called spooky action at a distance, further erodes the seemingly solid barriers between what was, what is, and what will be. Time is something we perceive. It is something we experience, and this experience is subjective. Consider the unreliability of eyewitness testimony. After a crime, multiple witnesses will offer conflicting accounts of what they saw, what they heard, how long it took. Yet they all agree that something happened. The same is true of time. We may disagree on its pace, on its nature, but we all agree that it exists. It is a something. And if it is a something, it must possess energy. It must have a wave function, a quantum signature that is deeply entangled with motion, with the observer, and with the very quantum continuum that underlies all of reality. Time has a fluid, almost liquid consistency. Imagine it as a vast, cosmic ocean. Innumerable futures and pasts exist within it simultaneously, like different currents and depths, all in motion. And we, as observers, are like ships sailing on this ocean. We reside on planets that spin on their axis and orbit their suns. Our sun orbits the center of our galaxy, and our galaxy itself is moving, drifting through the universe. We are constantly moving through space-time, constantly encountering different regions, different currents of time, and it is all relative. An observer on a planet in a distant galaxy is on their own ship, in their own current, experiencing their own now. This cosmic ocean is not flat. The journey is not always in a straight line. The Earth orbits the Sun in a gentle, continuous curve. Our solar system follows a curving path as it orbits the galactic center. Einstein and the mathematician Kurt Gödel extrapolated this principle to the universe itself. Space-time is curved. Light, and therefore time, must follow that curvature. Because of this fundamental curvature of reality, it is possible to travel in a great circle and arrive back where you began. And if this is true for space, Gödel argued, it must also be true for time. Time itself may be a circle. The past leads inexorably to the future, and the future, on a grand enough scale, can lead back to the past. The fabric of space-time is not just curved, but warped and distorted, puckered and stretched by the varying mass and gravity of planets, stars, and galaxies. Gravity and space-time are fundamentally linked to motion. Therefore, as velocity and gravity increase, they can not only curve, but shrink space-time itself. This concept, known as Lorentz contraction, is one of the keys to time travel. Imagine two chairs sitting at opposite ends of a large carpet. To move one chair to the other, you must cross the full distance. But if you were to scrunch the carpet together, folding it up and over itself, the two chairs could be brought very close together. In the same way, the immense gravity of celestial objects, or the extreme acceleration of a time machine, could scrunch up the fabric of space-time, bringing distant places and distant times, the present and the future, closer together. If the forces of mass and gravity are sufficiently powerful, the fabric of space-time doesn't just warp, it can rip. Holes can be punched through it. These theoretical rips and holes, created by immense gravity and extreme curvatures, could form passageways or tunnels between the folded layers of space-time. Physicists like Kip Thorne and Stephen Hawking have theorized that if a time traveler could enter and navigate these tunnels, these wormholes, they might be able to voyage from one distant location to another, from one galaxy to the next, and from the present to the future, or even to the past or a parallel universe, at effective velocities far exceeding the speed of light. Any time traveler who hopes to visit the future must accelerate their vessel towards, but always remain just below, the speed of light. As their velocity increases, the distance between their present and their desired future contracts, and that future arrives more quickly relative to the clocks of those they left behind. However, for those who seek the past, a more profound barrier must be broken. They must shatter the cosmic speed limit. For it is only at velocities in excess of the speed of light, in the superluminal realm, that time itself is believed to flow backward, and with it consciousness and memory may also reverse, and like a memory, the past itself decays. The further back one travels, the more frayed and indistinct the tapestry of reality might become. Time, as we have seen, is relative to the observer, but it is more than that. The experience of the past, the future, and the present are shaped and affected by a multitude of factors. Distance, gravity, acceleration, all play their part. But so too does our own consciousness, our mood, our surroundings. Time seems to speed up under conditions of great pleasure and joy, and it slows down, sometimes seeming to split apart or even run backward, under the influence of intense fear and terror. This is not just a mental trick. Acceleration, a key component of the fight-or-flight response, physically contracts space-time, causing it to speed up or slow down, depending on the observer's frame of reference. Consciousness itself can accelerate, especially under conditions of terror, and in these moments, time can dilate, and there can be a splitting of the self, a sense of watching oneself from the outside. While some might dismiss these experiences as mere, quote, mental distortions, the intertwined principles of relativity and quantum physics suggest they may be reflections of a deeper, more fundamental truth. Einstein himself, with his characteristic wit, captured this relativity of experience perfectly. "Put your hand on a hot stove for a minute," he said, "and it seems like an hour. Sit with a pretty girl for an hour, and it seems like a minute. That's relativity. Our inner world, our consciousness, is not separate from the physical world. It is entangled with it. The future and the past are shaped and affected by consciousness, which can influence events simply by observing them. This is the core of Heisenberg's well-established uncertainty principle and the phenomenon of quantum entanglement. Consciousness is not a passive observer of the universe. It is an active participant woven into the quantum continuum. Our awareness of the present could be likened to an event horizon, that boundary around a black hole from which nothing can escape. The future flows toward this event horizon of consciousness at an accelerated rate, approaching the speed of light, while the past recedes beyond it, at velocities increasingly greater than light speed. The event horizon of our consciousness, like that of a supermassive black hole, is a kind of eternal now, a state of being at the speed of light. And then there is the mysterious realm of dream time. In our dreams, the rigid laws of the waking world dissolve. Past, present, and future can be juxtaposed simultaneously, a swirling gestalt of memories and premonitions. The three dimensions of space become fluid and untethered. Hours can pass in what feels like mere seconds of clock time. Dream time, and the dream consciousness that experiences it, do not obey the laws of classical physics or even Einstein's relativity. They operate in the quantum realm, the domain of multiple worlds and infinite possibility. We conceptualize space-time as the fourth dimension. But perhaps this is too simple. Perhaps instead of a four-dimensional universe, with 3 dimensions of space and 1 of time, there are 6, or even more. 3 dimensions of familiar space and 3 intertwined dimensions of time. The objective, physical space-time of relativity, the subjective, experiential conscious time, and the surreal, non-linear dream time. All 3 of these temporal dimensions might be subject to contraction and dilation, speeding up and slowing down, independently of one another. When compared to the 10, 11, or more dimensions proposed by string and superstring theories, a 6-dimensional model of reality may seem almost conservative. These are but some of the profound and fascinating conundrums of time travel. They challenge our most basic assumptions about reality, causality, and the nature of our own existence, inviting us to contemplate the deep and quiet mysteries of the cosmos. There is no universal now. This simple yet world-altering statement from Einstein lies at the heart of our modern understanding of time. Time is relative, and so too are the futures, the presents, and the pasts, which all overlap and exist simultaneously in different, distant regions of the vast expanse of space-time. The present for one observer on one world can be the distant past or the unreachable future for another observer on another planet in another galaxy. Let's imagine a simple scenario. An astronaut on Mars fires a signal flare at the exact same moment, according to their synchronized atomic clocks, that an astronaut on the Moon fires theirs. For a team of observers orbiting Mars, the Martian flare will undoubtedly appear to have been fired first. Its light has less distance to travel to reach their eyes. But for observers back on Earth, the light from the Moon's flare will arrive first, and they will conclude with equal certainty that the lunar event happened first. Even if all teams were equipped with the most precise atomic clocks imaginable, those clocks would not agree. The clock on the Moon, the clock on Mars, and the clock on Earth would all tick at slightly different rates, influenced by the different gravitational fields and velocities of their respective locations. This is not just a thought experiment. In 1971, 2 physicists, Joseph Huffley and Richard Keating, performed a real-world test. They placed atomic clocks on commercial airliners and flew them around the world, first eastward, in the same direction as the Earth's rotation, and then westward, against it. When they compared these traveling clocks to a stationary reference clock back on the ground, they found that the eastward flying clocks, which had a higher effective velocity, had lost time. They had slowed down by an average of 59 nanoseconds. The westward flying clocks, with a lower velocity, had gained time. This elegant experiment was a direct confirmation of Einstein's predictions. Time, like the weather, is affected by local conditions. Under conditions of increased speed and increased gravity, time itself slows down. Atomic clocks are the most precise timekeeping devices ever created by humankind. They measure time by the incredibly stable and regular vibrations of light waves emitted by atoms of the element cesium. Their accuracy is measured in billionths of a second. Yet, even these paragons of precision are not absolute. They are susceptible to their environment. They run slower under conditions of increased gravity or acceleration, the very same conditions that would, theoretically, enable a time traveler to journey into the future. Locally, within a small frame of reference, it is relatively easy to agree on the sequence of events. Witnesses to an event in the same room can generally agree on what happened first, second, and third. But as the distance between events and between observers increases, the very notion of here and now becomes fuzzy and cannot be easily compared to there and then, or even there and now. The universe has no single, privileged now. Time, being a fundamental aspect of the universe, must have energy. Einstein's most famous equation, E equals mc squared, reveals the deep equivalence between energy and mass. Mass can be converted into energy, and energy can be converted into mass. Because of this, space-time itself is not an empty void. It is a substance with properties of both energy and mass. This is why it can be warped by gravity, and why it contracts in response to acceleration. It has a physical reality. Time is intimately associated with light. Light itself, with its curious particle-wave duality, travels at a maximum velocity of 186,282 miles per second in a vacuum. But time is not light, and light is not time. Rather, light acts as a messenger, carrying images, information, reflected from or emitted by innumerable locations throughout space-time. It is the vehicle by which we perceive distant moments, and time itself is perceived by an observer. For most of human history, we have measured its passage by the grand celestial clocks, the phases of the moon, the tilt and rotation of the Earth that give us our seasons, and the steady turning of our planet that marks the 24-hour day. Time, in our experience, is cyclical. It is a circle that we segment into years, months, weeks, days, hours, minutes, and seconds, measured by devices from ancient sundials to modern atomic clocks. And time, like the space it inhabits, is curved. Just as a massive object like our sun can bend the path of light, so too can it bend the flow of time. And just as tremendous gravity can physically shrink the stature of a person, so too can it shrink the circle of time, forcing more moments into a smaller, more compressed space. If the distance on a clock face between 12 noon and 12 midnight were to physically contract, it would take less time for those 12 hours to pass. It is this phenomenon, this gravitational and accelerative contraction of time, predicted by both Hendrik Lorentz and Albert Einstein, that forms the theoretical bedrock of time travel into the future. The very concept of a clock is relative. A day on Earth is 24 hours long, a consequence of our planet's rotation, but on Jupiter, a day lasts only 9.9 hours. On Mercury, a single day is equivalent to more than 58 Earth days. And on Venus, a day is even longer, stretching to 243 Earth days. Each world has its own clock, its own rhythm. We must not grant our terrestrial clocks a godlike, absolute status. It is a profound mistake to claim that there is no duration of time other than what can be measured by clocks. To truly understand the nature of time, we must include all its measures, including the biological and psychological clocks within us. After all, the very act of observation, of measurement, can affect and alter local events within the quantum continuum, and that continuum includes time. There is biological time, the rhythm of our cells and our bodies. There is conscious time, the subjective flow of our thoughts and emotions. And there is dream time, the surreal landscape of our sleeping minds. These different streams of time are seldom in perfect synchrony with the mechanical ticking of a clock. They can speed up or slow down depending on our mood, our level of excitement, or our state of boredom. And the same can be said for the innumerable locations in space-time, each with its own now, where past, present, and future overlap in a complex cosmic dance, all relative to observers on distant planets, stars, and galaxies. Consider for a moment the night sky. When you gaze at the moon, the light you see is not from the present moment, it is from just over 1 second ago. The sunlight that warms your face is a reflection of the sun, as it was 8 minutes in the past. And when you look at the nearest star, Alpha Centauri, the faint twinkle you see is an image from over 4 years ago, for that is how long it took its light to cross the vast emptiness of space to reach your eye. Even in your own home, you are constantly looking into the past. If you stand in front of a mirror, just 3 feet away, the light reflecting your image must travel from you to the mirror and back to your eyes. Since light travels at about 1 foot per nanosecond, the person you see in the mirror is you as you looked 6 nanoseconds ago. You are always fractionally younger in a mirror. Mirrors, in a very real sense, are gateways to the immediate past, an image of what was, experienced in the present. And the universe itself may be filled with such mirrors, tunnels into the past, what Einstein and Rosen theorized as bridges connecting our universe to a mirror universe on the other side. An image from the past, carried on a beam of light, is experienced in our present. But before that image arrives, while it is still traversing the space between its source and our eye, it is, relative to us, in the future. A sunbeam that has just left the surface of the sun will not arrive on Earth for another 8 minutes. Until it reaches us, that sunbeam is a future event. Now, imagine an alien observer on a planet orbiting Alpha Centauri, gazing at our Earth through a fantastically powerful telescope. The present moment on their world would overlap with Earth's past. They would be seeing an Earth from 4.3 years ago. They might be watching events from what we now consider our history. The reverse is true for us. The past, the future, and the present are all relative to the observer's position and motion in space-time. The images of Alpha Centauri, carried by light, are always of the star, as it was 4.3 years ago. Therefore, an image of Alpha Centauri from just 3.3 years ago is currently in transit, speeding towards us through space, and will not be received on Earth until a future date, 1 year from now. This particular future, the image of a more recent past of Alpha Centauri, already exists. It exists in a distant location, moving across space-time, and will arrive in our present in 1 year. The past can become the future, and both can exist before they arrive in the present, only to become the past once more, creating a continuous looping circle of time. The entire prospect of time travel, as built upon the foundations of quantum physics and Einstein's relativity, requires that a past and a future exist simultaneously, albeit in different, distant locations, separated by varying distances, all in motion within the dimension of space-time. And just as the natural circle of time is one of a future that becomes the present and then the past, the same is true for the mechanics of time travel. The journey to the future is the necessary first step for the journey to the past. It is only by accelerating towards the speed of light into the future that a traveler can earn the possibility of returning to the past, but only if they can then exceed that ultimate cosmic speed. Past, present, and future are relative, and they overlap. If the past and the future were not actual locations in space-time, flowing in various directions, we could not see images of stars from long ago. If a time traveler could accelerate fast enough to overtake the very beams of light carrying the mirrored image of Earth on their way to Alpha Centauri, they would witness an Earth from the past. But to do so, they would have to travel faster than light itself. If a space-time traveler were voyaging somewhere in the void between Earth and Alpha Centauri, no matter their velocity, they would encounter light images from Earth's past before those images could arrive at their future destination in Alpha Centauri. Once those light beams passed the traveler, they would be in the traveler's past, but still in the future for any observer in the Alpha Centauri system. Likewise, the traveler would come into contact with beams of light reflecting the images of Alpha Centauri before they arrived on Earth. So from the perspective of an observer back on the home planet, the time traveler would be encountering multiple futures which have not yet arrived on Earth or Alpha Centauri. But it is only upon accelerating beyond the speed of light that the time traveler could actually catch up with the light that has already left Earth or Alpha Centauri. And this is possible because acceleration itself shrinks space-time, pulling the future closer to the present. This is the fundamental principle of time travel to the future. By accelerating towards the speed of light, the very fabric of space-time contracts. The distance between the future and the present, between distant locations in space-time, shrinks. They become closer together, and the journey between them becomes shorter. If a time traveler departed from Earth on a long journey to Alpha Centauri and quickly achieved a velocity of 90% of the speed of light, the journey, from their perspective, would be drastically shortened. Instead of taking the 4.3 years it takes light, or the roughly 1569 days it would take at a constant sublight speed, the entire trip would be compressed to just 685 days, a journey of 1.87 years instead of 4.3. Because of this contraction of space-time, each day that passes inside the time-space machine at 90% light speed would propel the traveler 2.29 days into the future of Earth. 2.25 days on Earth would shrink to just 24 hours inside the time machine. When a time traveler accelerates toward light speed and journeys to the future, the flow of time in the world outside the machine will be profoundly different from the flow of time inside the machine. And the same is true for the traveler's biological time and conscious time. While time contracts and slows down inside the time machine relative to an observer on Earth, time on Earth speeds up relative to the observer in the time machine. This is because the contraction of space-time of distant locations occurs not for the entire universe, but specifically for the space-time occupied by the accelerating traveler. H.G. Wells' time traveler began his voyage in his laboratory, and from his unique vantage point, he could see the world outside accelerate. He saw events, people, and even a snail whiz by at impossible speeds. He watched his housekeeper, Mrs. Watchett, enter the room and walk towards the garden door. He surmised that it must have taken her a minute or so to traverse the space, but to him she seemed to shoot across the room like a rocket. Time, however, is relative. Although Mrs. Watchett, from the perspective of the time traveler, seemed to race across the room, if she could have peered into his machine, she would have seen him as if frozen, or moving with an almost imperceptible slowness. Wells's traveler also kept his eye on the laboratory clock. He noted that a moment before it had stood at a minute or so past 10. Now it was nearly 3:30. The clock outside the time machine was therefore ticking away at a rapid rate, relative to his own clock inside. His clock, from the perspective of Mrs. Watchett, would have been running incredibly slowly. This is precisely what Einstein's theories of relativity predict. When a time traveler accelerates towards light speed, the world outside becomes a blur of fast-forwarded moments. Time inside the machine slows to a crawl relative to the outside world. This affects biological time, conscious time, every process down to the atomic level. Imagine a corridor that is 30 feet long. For someone outside the time machine, it takes a certain amount of time to walk those 30 feet. But for the time traveler, due to the contraction of space, that same corridor might now only be 10 feet long from their perspective. They need only walk 10 feet, while the person outside still has to cover the full 30. Because their clock is also running more slowly, and since more time from the outside world has been contracted into their smaller, compressed space, it might take them only 10 minutes of their time to travel 30 minutes into the future. By contrast, it takes those outside the machine longer to get to that same future, because for them, it is further away, and their clocks are running faster, ticking off more seconds to cover the same temporal distance. This is the essence of the famous twin paradox. A time-traveling twin will age less than the twin who remains behind on Earth. Relative to each other, time and the aging process speed up for the Earthbound twin, while time and aging slow down for the twin in the time machine. Because space-time has contracted, and because it now takes less time to reach distant temporal locations which are now closer together, the time-traveling twin arrives in the future, having experienced less time, and therefore less aging, than their sibling back on Earth. There are at least 3 dimensions of space that we experience in our daily lives: length, width, and height. And there is at least 1 dimension of time, which, when woven together with space, creates the fabric of space-time. Time in one location is different from time in another. The future, the present, and the past can all exist simultaneously in different, overlapping locations within this fabric. And this fabric is not rigid. It can be twisted, folded, curved, and even shrunk. Space-time is elastic. When you increase your speed, your mass effectively increases as energy is converted into mass, and this in turn increases your gravitational influence. This increased mass and gravity squeezes space-time, causing it to curl up and contract. For example, a 100-pound woman who stands 5 feet 2 inches tall on Earth would weigh 235 pounds on a planet the size of Jupiter, and her height would shrink by approximately 16 inches due to the immense gravitational pressure. Gravity pulls, it does not push. In the same way, acceleration increases mass, which in turn increases gravity, and this gravity causes space-time to shrink. As a consequence, the distance between the present and the future decreases. They are pulled closer together because the space between them has contracted. Distant locations in space-time are no longer so far apart. Let us imagine a newly married couple. The bride is sitting shyly on one end of a 10-foot-long carpet laid out on a hardwood floor. Her husband sits at the other end. He is thinking about their immediate future together. He takes his rope and playfully lassos her around the waist. As he begins to pull her towards him, the carpet between them begins to curl and fold, creating a series of crests and valleys, a carpet warp. The far edge of the carpet and his bride still sitting upon it are being pulled closer and closer. The husband is like the time traveler in the present. His bride is the future, but he does not move toward the future. The warp in the carpet, the contraction of the space between them, has caused the future to move closer to him. Space-time can be stretched, shrunk, and it may curl up in response to tremendous speeds and gravitational influences, like skin that has been wrinkled by too much exposure to the sun. In this way, one layer of space-time may fold up and over another, such that distant locations come to be side by side or even face to face. Think of an accordion. When the bellows are squeezed together, the 2 handles, which were far apart, are now brought close. Or, think of the ocean. In a calm sea, 2 points on the surface are separated by a great distance. But when a wave forms, those 2 points can be lifted up to the crests of adjacent waves, momentarily side by side. Because the future, the present, and the past may already exist simultaneously in different locations in space-time, it could be argued that the time traveler, accelerating toward the speed of light, does not actually travel into the future. Rather, because of this folding, this contraction, this curvature of space-time, it is a future location that arrives more quickly relative to the traveler's frame of reference. The contraction of space moves the future closer to him, and it is no longer so far away. However, for the future to arrive more quickly, it must already exist before it arrives. At a distance of 13.1 billion light-years from Earth, a galaxy named Z8_GND_5296 is among the most distant objects we have ever detected. Although light, distance, and time are not synonymous, The fact remains that the beams of light carrying the image of this galaxy are reflections of its incredibly distant past. However, each particle wave of this light, before it reaches Earth, is in the future from our perspective until the moment it is received and perceived. At that point, it is in our present, and then, as it continues its journey past us, it recedes into our past. Likewise, images of Earth carried on beams of light on their way to that distant galaxy are from our past, but they will not be received by any potential observer there until a date far in their future. Events from the past on Earth take place in the future of Z8_GND_5296. The future and the past are relative. To arrive at a future location in spacetime, according to Einstein's theories, requires the size and length of spacetime itself to contract. And this is precisely what happens as your velocity nears the speed of light. Different locations in the future, futures that are 100,000 years apart, 1 million years apart, 13.1 billion years distant, and so on, all become closer together. The journey between them does not take as much time, because time itself is relative and has also contracted. If a time traveler were journeying at 50% of the speed of light to the galaxy Z8_GND_5296, the intervening spacetime would contract by about 13%. So instead of a journey taking 13 billion years, it would now take only 11.41 billion years to get there from Earth. At a velocity of 99% of the speed of light, spacetime would contract by about 80%, and the trip would last a mere 1.8 billion years. Like an accordion being squeezed, spacetime would be compressed, and distant stars would no longer be so far apart. According to special relativity, time can beat at different rates depending on velocity and acceleration. Time is linked to the speed of movement. And as you move, space itself becomes compressed along the direction of that motion. As one accelerates toward the speed of light, space-time contracts and time slows down. Because the traveler's own velocity does not shrink, she can traverse this shrunken space more quickly than those she left behind. Although the fabric of space-time may curl up and shrink, her velocity and the speed of light itself remain constant. Nevertheless, as the traveler accelerates and increases her velocity, she is catching up with the speed of light, and so the flow of time itself seems to be reducing its speed relative to her own. Consider a train racing by at 100 miles per hour. If you are in a sports car cruising alongside it at just 30 miles per hour, the train seems to be moving very fast. But if you accelerate your sports car to 150 miles per hour, the train would now seem to slow down relative to your perspective. It will not be perceived as moving away as quickly. The distance between you and the train will contract and decrease, even though the train is still moving at the same speed as before. Likewise, speeding up and catching up with the speed of light causes time to slow down, even though the speed of light does not change. Although the velocity of the train, or the speed of light, remains the same, the faster you go, the slower time becomes, a dual function of your accelerating velocity and the contraction of space-time. If you in the sports car accelerate to 200 miles per hour, you will speed past the train, and the train will fall further and further behind. You, like the time traveler, will arrive at a future location more quickly and in less time compared to those still traveling by train, even though you are both traveling the same physical distance. Just as the velocity and the space between the train and the sports car may contract or expand depending on their different speeds, space-time itself may expand or contract relative to different observers and their velocities. One in the time machine, the other back on Earth. Speed, or velocity, is not itself affected by time travel. It does not contract or dilate. Therefore, since space-time contracts as one accelerates, and though time slows down for the traveler, their velocity is not affected. This allows them to journey across this shrinking space more quickly, to cover the distance between the now and the future more rapidly, simply because they are closer together. This increase in velocity also causes a shrinkage not only of space-time, but of the moving object itself, the time machine, which in turn increases the mass and gravity of that shrinking object, which then contributes further to the collapsing and contraction of space-time. According to Einstein's famous equation, E equals mc squared, mass and energy are two faces of the same coin. The energy an object acquires, due to its motion, will increase its mass. The faster an object moves, the greater its mass, and as its mass increases, it also shrinks, as gravity pulls it inward toward its new, more massive center. This increase in mass is only noticeable at very high speeds. At 90% of the speed of light, an object's mass will double. This increased mass creates increased gravity, which in turn contributes to the contraction of space-time. Acceleration also increases g-forces, and this centripetal acceleration increases gravity, which is a major factor in time dilation and the contraction of space-time. Increases in gravity not only squeeze and crush those subject to these forces, but they can squeeze space-time itself, causing it to contract. Thus, increases in speed, gravity, and g-force will slow time and shrink the time traveler and her time machine. Gravity can also warp space-time, causing it to curl up and contract. In consequence, the present and the future are pulled closer together. Distant locations in space-time are no longer so far apart, a direct result of increased speed and gravity. This is why, at 90% of the speed of light, 2.29 days on Earth shrink to just 1 day in the time machine. And why 7 days in the time machine at this speed would take the traveler 16 days into Earth's future. The distance between the present and that future has contracted, so the future arrives in 7 days instead of 16. Because the time machine, the time traveler, and any clocks inside it also shrink, the passage of time inside the machine also shrinks relative to the time outside. From the traveler's perspective, inside the machine, time passes at the same rate because everything has shrunk to the same degree. Time is relative. It is only an outside observer, at a safe distance, who would perceive that the traveler's clock has slowed and the traveler has grown smaller. By contrast, if the time traveler were to look out of the machine, it would seem that the outside observer has grown larger and their clock is ticking faster. If a clock ticks faster, more time will pass compared to a clock that ticks slower, where less time passes. Since the distance between the present and the future has decreased because of the shrinkage of space, and since the traveler's clock has slowed down, it takes the traveler fewer ticks of his clock to arrive at the future compared to those back on Earth. This shrinkage of space-time gives rise to the famous twin paradox. If one twin leaves Earth and accelerates toward the speed of light, that twin will arrive in the future, having experienced less time than the twin left behind. Because it took less of her time, the traveling twin does not age as much, whereas the twin on Earth ages at the normal rate. When they are reunited, the time-traveling twin will be younger. The precise relationship between time dilation and the contraction of space-time can be determined by a formula devised by Hendrik Lorentz. As the time traveler's velocity approaches the speed of light, the effect increases exponentially. At 25% of the speed of light, time and length contract by a mere 3%. At 50%, the effect is still modest. But at 99% of the speed of light, time is slowed by a factor of about 7. At 99.5%, the factor is 10. And at 99.999% of the speed of light, space has shrunk by a factor of 224. Since the traveler's velocity remains constant, she can cross this much shorter length of space in a much shorter period of her own time. If we accept that time and the speed of light are related, then if a traveler journeys at 80% of the speed of light, 1 day from their perspective would be the equivalent of almost 2 days back on Earth. If they achieve 99% of light speed, 104 days in the time machine would be the equivalent of about 2 years on Earth. At 99.9% of light speed, a single 26-hour day in the machine would be equivalent to 6 years on Earth. To experience a future 2,190 years distant, a traveler would have to spend just 1 year in their machine, traveling at 99.999% of the speed of light. The amount of contraction becomes truly dramatic as velocity approaches the speed of light. 9% of the speed of light. The amount of contraction becomes truly dramatic as velocity approaches the speed of light. At 99.999999% of light speed, almost 2 years pass on Earth for every single day in the time machine. And at an even greater velocity, just shy of the absolute limit, for every day on board, nearly 20,000 years might pass back on Earth. However, upon reaching the speed of light itself, time stops. And it is only upon accelerating beyond that cosmic limit that time runs backward, and the contraction of space-time continues in a negative direction. One must accelerate towards the future to reach the past. Space-time contracts, and so does the time machine, which becomes flattened in the direction of motion. The traveler and his vehicle shrink like an accordion. The paradox is that time speeds up outside the machine and slows down inside it. However, from the perspective of the traveler, time will not seem to have slowed down for them, but will appear to have sped up for the world they left behind. Nor will space appear to have shrunk, because the traveler and their machine have also shrunk to the same degree. All is relative. By contrast, those on Earth would perceive the time machine as shrinking as it speeds away, eventually contracting to less than the width of a hair. Likewise, the very space between points in space-time may shrink to less than the width of a hair. Because velocity remains unchanged, the traveler can journey between 2 points more quickly, because more of Earth's time is also being compacted and squeezed into a smaller space. The now and the future become closer together. Back on Earth, the distance to that same future remains the same, and it takes more of their time to arrive there. Therefore, the time traveler can reach the future more quickly than those on Earth. What all of this implies is that the future, or at least a multitude of futures, already exist, albeit in distant locations in space-time. Because of this contraction, the traveler does not really journey into the future. Instead, the future journeys to him at an accelerated rate, because the distance between them shrinks as he approaches the speed of light. Because of this dilation of time and contraction of space, once our traveler lands her machine back on Earth, depending on how fast and how far into the future she was propelled, she may find a world utterly changed. All her friends and relatives may be long gone, turned to dust centuries ago. A completely new generation, or even a new species of Earthlings, might be there to greet her upon her return. By contrast, since time slowed down for her, and since space-time was squeezed together, she, the traveler who arrives in this distant future, may not have aged appreciably. This is the heart of the twin paradox, a thought experiment based on special relativity. Because the clocks inside the time machine run more slowly, a time-traveling twin will age more slowly than her twin who remains on Earth. The Earth-bound twin will be much older, perhaps ancient, while the traveler is still in the bloom of youth. As Einstein himself summarized it, if we placed a living organism in a box, one could arrange that the organism, after any arbitrary lengthy flight, could be returned to its original spot in a scarcely altered condition, while corresponding organisms which had remained in their original positions had already long since given way to new generations. For the moving organism, the lengthy time of the journey was a mere instant, provided the motion took place with approximately the speed of light. Let's consider an example. A woman is born in the year 2100. She has a normal life expectancy of 80 years and would have died in the year 2180. But at the age of 20, in the year 2120, she embarks on a journey into the future. If she achieves a velocity just shy of the speed of light and arrives back on Earth in the year 2180, she would still be, biologically, only 20 years old, plus the time spent on her journey. Instead of facing the end of her life at 80, she is still a young woman of 20, with another 60 years of life ahead of her, now expected to live until the year 2240. This seemingly fantastical premise is supported by experiments with non-living, ultra-short-lived subatomic particles. The muon particle, for instance, which normally decays in a fraction of a second, is given a new lease on life when accelerated to 99.92% of the speed of light. Its lifespan is extended by nearly 25 times, and it travels 25 times further as a result. Other particles, like phi mesons, accelerated to similar velocities, also achieve significant lifespan extensions. Presumably, these particles live longer because they have arrived in their future more quickly than their slower-moving counterparts. Therefore, it is a reasonable prediction that a human time traveler journeying at near-light speeds should also live longer compared to the friends and relatives they left behind. These same principles apply to great journeys across space to other stars and planets. If the journey takes place at near-light speeds, the space-time traveler could visit a distant star and then return home, still fresh and young, while her relatives and friends on Earth will have grown old and infirm and may have already passed away. Let's imagine twin sisters. Gaia stays on Earth, while her twin, Aurora, travels at 80% of the speed of light to Proxima Centauri, which is 4.2 light-years away. For Aurora, the trip will take 5.25 Earth years. At her speed, 1 day in her time machine is equal to 1.67 days on Earth. So, her journey of 5.25 years, or 1,916 days, is equal to 3,200 days, or 8.76 years on Earth. Aurora's clock will tick almost 60% more slowly than Gaia's clock, and she will age only 3.15 years during her journey, while Gaia, back on Earth, will have aged 5.25 years. If Aurora immediately turns around and returns to Earth at the same speed, she will be 6.3 years older upon her return, while her twin sister Gaia will be 10.5 years older. From Aurora's perspective, however, something strange has occurred. To her, it was Earth and her sister Gaia who were traveling at 80% of the speed of light, because time moves more quickly outside the time machine relative to inside. So she is shocked, though perhaps delighted, to discover that it was she who remained more youthful. The difference in their perspectives arises because the twins did not have equivalent experiences. It is the twin who accelerates, who endures the g-forces, who experiences the contraction of space, who also experiences fewer ticks on her clock. The future and the past are not equivalent, nor are gravity and light in different locations and frames of reference. All are time asymmetric. Like the weather, time is not the same everywhere. Because the traveling twin, Aurora, experienced different gravitational conditions and differential speeds of acceleration and deceleration, the twins ceased to be twins in a symmetrical sense. They are no longer equivalent. The same would apply to twin atomic clocks. The clock on Earth will have recorded more ticks than the clock on the time machine, which runs slower. From Gaia's perspective, time slowed down for Aurora. And not just her clock. Aurora herself would have appeared to be moving very slowly, perhaps even frozen in time, as she accelerated away. Her time machine would also appear to have shrunk in size. By contrast, from Aurora's vantage point, Gaia would appear to have grown tremendously in size, and to be rushing by at a lightning-fast speed. However, neither of these women would have any sense of how she appeared to her twin, because their inertial frames of reference were no longer symmetrical. The size and motion of any object can only be described relative to something else. If all frames of reference were the same, it would be impossible to determine size or velocity. There must be contrast. If everything were wet, we would have no concept of dry. In a non-inertial reference frame, one that is accelerating, the laws of physics themselves vary. If Aurora's velocity in her time machine were constant, her speed of movement, relative to the machine, would be zero. Although the machine is speeding across the cosmos, she is moving with it, not faster or slower than it. She would feel no sense of motion, except by contrasting herself with the surroundings outside the machine. It's like being on a perfectly smooth train. You feel at rest, and it is the world outside the window that appears to be moving. This inability to distinguish a resting state from uniform motion constitutes an inertial frame of reference. Einstein's theory of special relativity assumes the equivalence of all inertial reference frames. All physical laws, including the speed of light, have the same form in every inertial frame. Therefore, Aurora would not sense that anything is different inside her time machine. It would feel normal, but the world outside and her sister Gaia would appear to her as speeding up and growing larger. Gaia, however, would have the exact opposite impression. Aurora would also be unaware of any slowing of her own time within the machine. This is because she, and the space-time she occupies, would have shrunk. The clocks in the machine, her own biological clock, even the speed of her consciousness, would have all been compressed and slowed to the same degree. From her point of reference, everything inside the machine is normal. It is the world outside that is changed. This combination of space-time contraction and the slowing of the traveler's clock could be called the Rip Van Winkle effect. It is like a state of semi-suspended animation, with each hour in the time machine corresponding to weeks, months, years, or even centuries back on Earth, depending on the near light speeds attained. And when Rip Van Winkle, or our traveler, finally awakens, they find themselves in a future they no longer recognize. But what would happen if a time-traveling twin journeyed into the past? Would she age in reverse? The only way to travel into the past is to first travel into the future. Time passes more swiftly as velocity approaches the speed of light, but at the very moment the traveler exceeds the speed of light, they would experience a time reversal. The contraction of space-time would continue, but in a negative direction. All clocks would begin to tick in reverse. And so the traveler headed toward the past might indeed age in reverse, becoming a teenager, then a child, an infant, a fetus, an embryo, and finally, back to the constituent sperm and ovum from which she was conceived. If this scenario is correct, a traveler could journey no further back in time than the moment of their own conception, or perhaps the moment their time machine was built. Or perhaps the opposite would happen. The aging process might be accelerated, and she might become as old as the time she visits. If she leaves the year 2200 and arrives in 2000, she may instantly become 200 years old, at least from the perspective of those she left behind in her own time. Or, perhaps more grimly, the backward journeying traveler might simply disintegrate and decay. Decay processes are what we associate with the past. That which is from the past decays. Memory of the past decays. The further back in time one goes, the more decay one might expect to find. To travel back in time, the speed of light must be exceeded. The clocks that had run increasingly slower as velocity approached light speed would stop at the precise moment of light speed, and upon exceeding that cosmic limit, these clocks would run backward, perhaps running faster and faster as superluminal velocities increase. In this scenario, she might grow older more quickly, or younger more quickly, or she might face a more existential threat, self-annihilation upon encountering her own double in the past, the problem of duality. She who travels backward in time already exists in that past. Unless the backward traveling twin is somehow transformed into a state of negative mass and negative energy, a transformation which may indeed occur upon exceeding the speed of light, then this duality would violate the fundamental laws of conservation of energy and mass. Upon encountering her past self, she and her double might self-annihilate. Or, if the negative energy twin from the future comes into contact with the positive energy twin from the past, the result could be equally catastrophic. Then there is the problem of miniaturization, a consequence of length contraction. Traveling backward in time poses many profound risks and may not be a successful means of finding the fountain of youth. So long as the time traveler is journeying at near light speed, her personal clock and her mind are slowed, and she ages more slowly compared to her twin on Earth. It is only when she reaches her destination in the future and slows her velocity that her clock and her mind would speed up again. From the perspective of an outside observer, the traveling twin would be slowly emerging from a kind of comatose state. It is only when her velocity decreases to a speed equivalent to that of Earth's that she awakens in the future, only to discover that her sister has aged while she has remained young. Unfortunately, although she may be younger, she may not be very healthy. The twin paradox, as derived from Einstein's theories, predicts that relative to the traveler, the twin on Earth will age more quickly. But is it really true that the traveler would have aged by only a fraction of that time? If the clock on board the time machine slows down, does one's biological clock also slow in perfect synchrony? Does the heart beat slower? Or is it possible that the incredible stress of time travel, the acceleration, the radiation, might actually cause premature aging? We have experimental evidence that atomic clocks at different altitudes will eventually show different times, a function of gravity's effect on time. The lower the altitude, the stronger the gravity, and the slower the clock. Clocks speed up as altitude increases and gravity weakens, albeit by incredibly small amounts, just a few nanoseconds. For example, if two identical clocks are separated vertically by just 1 kilometer, the higher clock will gain the equivalent of 3 extra seconds for each million years that pass. This speeding up of clocks at higher altitudes is due to a reduction in gravitational potential. As Einstein predicted, clocks run more slowly near massive objects where gravity is strong, and time dilates, running more quickly as gravity is reduced. There is more gravity closer to the surface of the Earth, and it decreases with increasing elevation. At 30,000 feet above sea level, your weight would decrease by a fraction of a percent, and your personal clock, if it were an atomic clock, would run infinitesimally faster. By contrast, you are heavier at sea level, and clocks run slower. Decreases in altitude and increases in gravity slow the clock down. Acceleration, however, effectively increases mass as energy is converted into mass, and this increases gravity. This increased gravity squeezes and contracts space-time, such that there is more time in a smaller space. But here we find a contradiction. Contrary to Einstein's predictions about the aging of the twin, the traveler may actually age more rapidly, precisely because of the forces that make time travel possible. Gravity, in our everyday experience, is not a friend to longevity. A time traveler, when accelerating toward the speed of light, would experience incredible increases in gravity due to their increased mass and the g-forces of acceleration. Yet, increases in gravity, although they slow the passage of clock time, do not seem to slow the aging process. In fact, they may speed it up. Studies of human populations have shown that those who dwell at higher altitudes, under slightly reduced gravitational influences, where clocks tick slightly faster, are generally healthier and live longer than those who live at sea level, where gravity is stronger. In one study, it was found that men living at a mean elevation of nearly 6,000 feet above sea level lived, on average, between 1 to 3.5 years longer than men dwelling at sea level. The same was found for women. Another study found that death rates from all causes were significantly lower in mountain populations than in the lowlands, even after accounting for other lifestyle factors. Of course, one could argue that high-altitude longevity has other causes, like lower oxygen environments or increased exposure to solar radiation, which helps synthesize vitamin D. But the correlation with gravity is intriguing. Lifespan seems to expand as elevation increases and gravity decreases. By contrast, our time traveler would experience immense increases in g-forces and a slower clock, as well as exposure to cosmic radiation. Based on these findings, one could predict that the traveler might age more rapidly, suffer more health problems, and die sooner than the twin she left behind. Yes, perhaps she would be chronologically younger, but she might be in a state of advanced biological decay. Longevity is also correlated with latitude. Just as lowlanders seem to die more quickly than highlanders, those living at higher polar latitudes, who are subject to increased gravity due to centrifugal forces and the slight flattening of the Earth at the poles, suffer more serious health problems than those dwelling in the equatorial regions. Gravity is slightly weaker at the equator, and just as increases in elevation correlate with increased life expectancy, decreases in latitude, moving closer to the equator, correlate with a reduced incidence of severe health problems like cancer. Increases in gravity, it seems, may not be good for one's health, and it is precisely these conditions that the time traveler must endure. The very forces that would propel him to the future might instead propel him to an early grave. To journey to the future or the past requires, first and foremost, a journey through space. As we've contemplated, our Earth and our entire solar system are in constant, rapid motion. A time machine that simply altered its temporal coordinate without altering its spatial one would be a death trap. But what if one could create a time machine that remains anchored, somehow tethered to the Earth as it moves? Presumably, under these conditions, everyone and everything on Earth would also be propelled to the future at the same rate as the traveler. All clocks would run at the same speed. The passage of time, being relative, would not change from what is experienced as normal. The traveler might as well be sitting on his couch. Such a machine is a fantasy, unless it could somehow manipulate the fabric of reality at the most fundamental, Planck-length scale, composed of miniature black holes with negative energy and mass. No, a time machine must be a spacefaring vessel. And this vessel would subject its occupant to prolonged periods of injurious g-forces while accelerating towards the speed of light. To travel into the distant future would require tolerating these high levels of g-force for days, weeks, months, or even years. For example, it would take a time traveler accelerating at a constant and relatively comfortable rate of 1 g, the gravity of Earth, 250 years, just to reach a speed of 99.9992% of the speed of light. The journey itself would be a life sentence. Therefore, to visit the past or the future of this planet, a time machine must also be a technologically advanced spacecraft, capable of incredible acceleration, of counteracting g-forces, of maintaining its velocity, and then of decelerating with precision to locate and land upon an Earth that now exists in a distant future or past location in the vastness of space-time. Even on the International Space Station, which orbits our planet, time behaves differently. Astronauts on the ISS are in a state of continuous freefall, which counteracts Earth's gravity, but they are also traveling at an incredible speed. The result is a slight contraction of space-time, and astronauts aboard the ISS are continually being propelled, ever so slightly, into the future. NASA astronaut Ed Lu estimated that for every 6 months spent aboard the station, an astronaut will age 0.007 seconds less than those on Earth. They are, in a very real sense, time travelers. But is it really true that these astronauts, and by extension our time travelers, would age more slowly in a biological sense? An astronaut hoping to visit the ISS must first escape Earth's gravity, experiencing increased g-forces during launch. Our time traveler would have to endure these forces for much, much longer. And time travel would subject the body to tremendous, unrelenting stress. Microgravity, as we know from our experience with astronauts, is not good for one's health. It results in decreases in muscle mass and bone density. And increases in gravity, as measured in g-force, can be a killer. Multiple studies have found that astronauts, when compared to people of similar age and background, tend to die at a younger age. They do not return to Earth from their missions looking younger and healthier, but often more like frail, older individuals who have difficulty standing, walking, and maintaining their balance. G-force is a measure of acceleration. At 1 g, we feel normal. At 2 gigaseconds, we feel twice as heavy. Experienced fighter pilots can withstand up to 9 gigaseconds, but only for a second, after which they black out or die as the pressure crushes their bodies and internal organs. Death is the likely outcome if subjected to 6 gigaseconds for more than a few seconds, or 5 gigaseconds for more than a few minutes. Even prolonged exposure to 4.1 gigaseconds increases mortality and causes significant injury to the body. It causes incredible stress, injures internal organs, and increases metabolic requirements to the point where the body begins to consume itself for energy. Given our current and foreseeable technology, it is not possible for a human to instantly achieve the speed of light. The acceleration required would generate such incredible g-forces that any living organism would be reduced to a flattened smear of micromolecular ooze. Even if a traveler accelerated at a mere 25 gigaseconds, they would be crushed by over 5,000 pounds of pressure and would be dead long before reaching any significant fraction of light speed. If our traveler were to accelerate at a more survivable 3 gigaseconds, it would take them approximately 31 years to reach a speed just shy of the light barrier. A 20-year-old traveler would be 51 years old by the time they reached cruising velocity. Given the incredible, prolonged stress, it is unlikely they would be in good health, and they would still have to decelerate, a process that would take another 31 years. They would have to turn their ship around, a maneuver that would generate its own incredible G-forces, and aim to intercept a future Earth, thousands of years in the future and billions of miles away. Upon stepping out of their machine, our traveler would be over 82 years old and would likely need a wheelchair, if not a coffin. Then there is the problem of fuel. The Saturn V rocket that propelled men to the moon carried over 5.5 million pounds of propellant. A time machine would need to reach a velocity of over 185,000 miles per second. The fuel requirements alone, using conventional technology, would make the journey impossible. Perhaps, as our technology develops, these problems can be overcome. It may become possible to harness the power of matter-antimatter annihilation, releasing tremendous amounts of energy. Or perhaps a warp drive could be created, a vessel that doesn't move through space but moves space around it by creating a bubble of negative energy in front of it and positive energy behind it, allowing it to ride a wave in the fabric of space-time without experiencing any internal acceleration. Or it may become possible to exploit the incredible amounts of energy contained in the quantum foam, in spaces smaller than a Planck length. In this realm, a trip of 1,000 years into the future might require less than 1,000 pounds of highly condensed energy. In fact, like space-time itself, as the time machine accelerates, it would contract, and, at near light speed, it might become smaller than a Planck length and blow a hole through space-time itself, allowing it to tunnel through to the past, the future, or any mirror universe that may lie on the other side. According to Newton, gravity is a force, an invisible rope that reaches across space to pull objects together. Einstein rejected this view. He argued that nothing, not even a force, can travel faster than the speed of light, so gravity could not act instantaneously across vast distances. Instead, he proposed something far more radical. Gravity is not a force. It is a consequence of the geometry of space itself. The presence of matter and energy causes the fabric of space-time to curve, to warp, and it is this curvature that dictates how objects move. It is the contiguity of objects, all connected by the same underlying fabric of space-time, that accounts for these seemingly instantaneous effects. Matter tells space-time how to curve, and curved space-time tells matter how to move. The movement of a time machine through space, its acceleration, produces energy, and this energy is absorbed by the machine and transformed into mass. As the traveler accelerates, greater amounts of energy are absorbed, increasing the mass and thus the gravity of the traveler and their machine. And this increasing mass and gravity, in turn, further warps the geometry of the surrounding space-time. It is a feedback loop. This increased mass also makes it harder to maintain speed or to accelerate further, but it also slows the flow of time and causes space to shrink. The future and the present are pulled closer together. Even with a reduced effective speed, the traveler can still rush to the future in less time than those back on Earth. A clock will tick more slowly as it approaches a source of gravity. A clock on a planet with the gravity of Jupiter would run slower than a clock on Earth. This gravitational time dilation has been confirmed in numerous experiments. The increasing gravity and mass of the time machine itself would also contract and curve the surrounding space-time, but its effects would be local, confined to its immediate vicinity. The curvature of space-time is not uniform. It is described by a complex mathematical object called the Riemann curvature tensor, a collection of 10 numbers defined at each point in space. These equations show that space-time is curved differently at specific locations, depending on the density of mass and energy in that region. In this view, the universe would not be a perfect, smooth sphere, but a lumpy, textured object, filled with innumerable cavities and folds, created by the mass and gravity of various stars and galaxies. If the entire universe is curved, as Einstein's theories predict, it implies something profound. Just as traveling in a straight line on the surface of our curved Earth will eventually bring a traveler full circle back to their starting point, the same could be applied to a journey across the curved universe. And this would apply not just to space, but to light and to time itself. Time may be a circle, a great cosmic clock, ticking at different speeds in different places. The mathematician Kurt Gödel, a friend and colleague of Einstein's, explored this very idea. In what is now known as a Gödel universe, there is no absolute time. Time can circle back on itself in endless loops, making it theoretically possible for a time traveler to journey in a great circle back to the point in space and time from where he started, even returning to the moment of his own birth. In regions of relativity, with a sufficient concentration of energy and matter, space-time can bend and contract to such a degree that distant locations can curl up right next to each other, making time travel seem almost inevitable. Because of this bending, this folding and contraction, the distance between the future and the present shrinks, like two distant points on a map that are brought together when the map is folded. And if gravity is strong enough, it can create more than just depressions. It can form deep holes in the fabric of space-time. The weight and mass of a great galaxy can cause such a deep curvature that it drags all of the surrounding space-time down with it, into a cosmic pit. If two such galaxies are near each other, the pits they create can be drawn together, and the distance between them, measured in a straight line, shrinks dramatically. The planets in our solar system orbit the Sun not because of an invisible force of attraction, but because they are following the curved paths, the grooves, carved into the fabric of space-time by the Sun's immense mass. It is a cosmic roulette wheel, and the planets are the balls, rolling along the tracks laid down by gravity. Empty space itself can be warped. Gravity alters the path not just of planets but of light. Light bends as it follows the curvature of space-time. Since time is a part of this fabric, it too must be bent by gravity. An accelerating elevator, for example, creates an artificial gravity, and a beam of light shown across that elevator will appear to bend downwards. Acceleration and gravity can curve and bend light, and this has been confirmed by observing the light from distant stars as it passes near our Sun. The starlight is deflected, its path bent by the Sun's gravity, and this bending of light can lead to strange and beautiful optical illusions on a cosmic scale. Light from a very distant galaxy can be split apart and bent by the gravity of another galaxy, or a cluster of galaxies that lies in front of it. This phenomenon, known as gravitational lensing, can create multiple, distorted images of the same distant object as the light is split and coiled around the intervening mass. If light, which carries the images of the past, can be warped and split, perhaps the past itself can be warped and split. And since that light, before it reaches us, is in our future, perhaps the future too can be bent and split apart. The universe then is not a single uniform flow of time, but a place of innumerable pasts, futures, and nows, some of which may arrive side by side, some one after the other, and some which may even curl around such that the future leads back to the past. Einstein theorized that time and space can be unified in a fourth dimension, two aspects of the same fundamental quantity. Space can be converted into time, and time into space. Time, therefore, must have energy, and if it has energy, it can have potential mass. It shares characteristics with light and may have a particle-wave duality. If the entire universe is curved, then a journey in a straight line across the cosmos will bring a traveler full circle. And if this is true for space, it must also be true for time. Time itself is a circle. The present leads to the future, and the future eventually leads to the past. The mathematician Kurt Gödel explored this very idea. Using Einstein's own field equations, he discovered that a particle traveling through a curved spacetime would circle around from the present to the future and then continue on its path to meet itself in the past. From the past, it would circle around to meet itself in the future, an infinitely repeating pattern. Gödel argued that because space-time is curved, the future and the past must also be curved, circling back on themselves to form an endless loop. Time is a circle. By making a round trip on a rocket ship in a sufficiently wide curve, he wrote, "It is possible in these worlds to travel into any region of the past, present, and future and back again." This concept of a rotating universe filled with what are called closed time-like curves, or CTCs, would shatter our conventional understanding of causality. If time can circle back on itself, then the future can affect the past. Effects could precede their causes. The future could influence the present and the past. It is a world where, hypothetically, you could be punished as a child for a transgression you will commit as an adult. This circularity also implies multiplicity. Because gravity can bend and split the light from distant objects, the light reflected from our own Earth may also be split apart as it curves through space. These beams of light, these time-light images, could be curved around massive galaxies and reflected back towards us, becoming mirror images of our own planet's past. As we gaze up at the twinkling stars in the night sky, some of those points of light might not be distant suns at all, but faint, ghostly images of our own solar system from a time long ago. And in a Gödelian spinning universe, the mirror would also be gazing back. This Earth could itself be a mirror image of a past, a reflection that those on a future Earth can look back upon. A closed time-like curve is a world line in space-time that loops back on itself. A particle, or a time traveler, on such a path would eventually return to their exact starting point in both space and time. It is a journey that is both forward and backward in time. If CTCs exist, then travel into the past is not just possible, but perhaps inevitable. The only way to achieve this, according to Einstein's own theories, is to exceed the speed of light. It is only upon accelerating into the future, and then pushing beyond the light barrier, that the contraction of space-time continues in a negative direction, and time flows in reverse. The future leads to the past. If time is a circle, then effects cannot always be traced to an earlier cause, for the cause may lie in the future. An event can be simultaneous with its cause, or even occur before its cause. An event might even be able to cause itself. These are not just fanciful thought experiments. We see echoes of this in the quantum world, in the phenomenon of entanglement, that spooky action at a distance that so troubled Einstein. It is well established that what we call causes and effects can occur simultaneously at speeds faster than light, a consequence of the deep interconnectedness of all things in the quantum continuum. The universe is not a perfect sphere. The distribution of galaxies is asymmetrical, with vast walls of galaxies clustered together, separated by immense voids. This clustering contributes to the unequal distribution of gravity, which causes space-time not just to curve, but to fold and curl up, asymmetrically affecting the flow of time. And the very patterns we see in nature, from the spiral of a seashell to the spiral of a galaxy, suggest a deep, underlying rotational symmetry to the cosmos. Electrons orbit the nucleus of an atom. Planets orbit the sun. Our sun orbits the supermassive black hole at the center of our rotating galaxy. It is logical to assume that the universe itself may be in a state of general rotation. Recent observations of the most distant supernovae seem to support this. They are moving away from us at an accelerating rate, which could be interpreted as evidence for an expanding universe driven by a mysterious dark energy. Or it could be interpreted as evidence of a rotating universe, where these distant objects are simply closer to the central axis of rotation and are therefore moving at a faster velocity, just as the inner planets of our solar system move faster than the outer ones. If the universe is rotating, then time itself is a circle, and the journey from the future to the past is woven into the very fabric of reality. And if time and light can follow a closed, circular path, then images of Earth from long ago may be mirrored throughout the cosmos. There could be windows into our own past scattered across the night sky, showing us the age of dinosaurs, the building of the pyramids, or perhaps even resolving some of history's greatest mysteries. Time is a circle, a journey that takes the voyager to the future and upon exceeding the speed of light, carries them from that future back into the past. And upon reaching that ultimate speed, the traveler and their machine may shrink to such an infinitesimal size, with such concentrated mass and energy, that they punch a hole in space-time itself, a hole through which they can journey to a mirror universe on the other side. The immense gravity of celestial bodies creates depressions, or pockets, in the fabric of space-time. The gravity of Earth is stronger at sea level than at higher elevations, and stronger still towards the planet's core. All falling objects are drawn towards this center of gravity. If our Earth, with all its immense mass, were to collapse and implode upon itself, its gravity would increase exponentially. Time on its surface would slow to a crawl. If it continued to shrink, say, to the size of a golf ball, it would retain the mass and gravity of an entire planet. No light would be able to escape its surface, and time itself would stop. It would become a black hole. But what if the shrinkage continued? What if it became smaller than an atom, smaller than the fundamental unit of measurement known as the Planck length? In this realm, the laws of physics as we know them break down. But it is here, in this infinitesimally small space, that time reversal is predicted to occur. The gravity becomes so powerful, the energy so concentrated, that it blows a hole through the tissues of space-time, a tunnel that leads from the present to the past at superluminal speeds. These holes in space-time, these Einstein-Rosen bridges, could offer a passageway to the future, to the past, or to a mirror universe on the other side. The cosmos is believed to be littered with such holes, from those smaller than an atom to the supermassive black holes that lurk at the center of galaxies, possessing the gravity and mass of billions of suns. To journey into the past, a time traveler could attempt to shrink themselves to a microscopic size, or they could dive their time machine into one of these cosmic behemoths. For according to Einstein and Rosen, the hole has no bottom, it tunnels through to another reality. A supermassive black hole is the remnant of a colossal star that has exhausted its nuclear fuel and collapsed under its own immense gravity. It creates such an intense gravitational field that nothing, not even light, can escape its pull once it crosses a boundary known as the event horizon. The singularity at its heart may be no larger than a marble, but it contains the concentrated mass of a billion suns. Tens of millions of smaller, stellar mass black holes are thought to populate our own galaxy. And there may be even larger ones, with the gravity mass of millions of entire galaxies, like the Eridanus black hole, a cosmic spider that has consumed everything in its billion light-year vicinity. These holes in space-time not only suck in light, but they may also act as mirrors into the past, or as windows into mirror galaxies. A time traveler could dive their machine into one of these holes, be accelerated to faster-than-light speed, and enter the mirror at the bottom of the hole that leads to the long ago. Such a journey, of course, is fraught with peril. The traveler might be crushed to death by tidal forces, disintegrated into a stream of particles, or irradiated into ash. Objects approaching the event horizon are drawn into a vortex, their velocity accelerating towards the speed of light. For them, time would contract, and they would be flung into the future. Upon reaching the event horizon itself, their velocity would be the speed of light, and time would stop. They would exist in an infinite now. And if they were to pass beyond the event horizon, into the hole itself, their velocity would increase beyond the speed of light, and they would be sucked into the past. The interior of these holes may be a realm of negative energy, a vacuum with an energy density lower than zero. If a time traveler were to enter such a space, they might be stripped of their positive mass and energy, emerging at the other end of the hole as a being of negative mass and negative energy, miniaturized and perhaps ghost-like, forever repelled by the positive energy world they sought to visit. And yet, there may be another way. The traveler does not have to fall into the hole. They could use its immense gravity and the swirling vortex of space-time around it as a cosmic slingshot. By approaching a spinning black hole in a carefully calculated trajectory, the time machine could borrow the hole's rotational energy, accelerating to near-light speed and into the future, and then, with a final gravitational kick, be flung beyond the light barrier and into the past. The journey to the past requires a journey to the future first. It is a seeming paradox. As a traveler accelerates towards the speed of light, space-time contracts, and the future arrives more quickly. At the speed of light, time stops in an eternal present, an event horizon separating what was from what will be. And at a velocity just beyond the speed of light, the traveler crosses that horizon, and the journey into the past begins. The time traveler, upon accelerating beyond the speed of light, may also undergo a fundamental transformation. As their velocity increases, their mass increases, and their physical form contracts in the direction of motion. At near-light speeds, the traveler and their machine might shrink to the size of an atom, or even smaller, to less than a Planck length. In this state, they would possess such incredible, concentrated mass and energy that they might blow their own hole in space-time, emerging on the other side with negative mass and negative energy. This dual state, the positive energy traveler heading to the future and the negative energy traveler emerging from that future into the past, could resolve the paradox of conservation of energy. No new mass or energy is created because the positive is perfectly balanced by the negative. However, this duality presents its own dangers. The traveler may be continually passing themselves, one coming and one going, on parallel tracks of time. And if these two selves, one of matter and one of antimatter, were ever to collide, the result would be mutual annihilation. This strange, superluminal state, a being of negative energy and negative mass traveling from the future to the past, is reminiscent of a hypothetical particle known as the tachyon. Tachyons, if they exist, are believed to always travel faster than light, forever journeying from the future into the past, violating our conventional notions of causality. They are the true time travelers of the quantum world. And this brings us to the profound and strange world of quantum mechanics, where the solid, predictable universe of our senses dissolves into a shimmering sea of probabilities. Here, the very act of observation changes what is observed. The past, the present, and the future are not fixed points on a line, but entangled states in a universal wave function. This wave function describes all possible states of the universe, which leads to the many worlds interpretation. Every quantum event, every choice, every observation may cause the universe to split into multiple, parallel realities, each representing a different outcome. In this view, a time traveler who journeys to the past and changes an event, say preventing an assassination, does not alter their own timeline. Instead, they have simply crossed over into a different branch of reality, a different world where that event never occurred. The grandmother paradox, killing one's own grandmother before she can give birth to one's parent, is resolved. The traveler would be killing the grandmother of a parallel self in a parallel world, a tragedy for that world, but one that would have no effect on the traveler's own existence. The past he left remains unchanged. He has simply chosen a different past to inhabit. And now, let us leave these deep and wondrous theories and return to a single human story. A story of one man, adrift in the many worlds of time. Half drunk, I was bundled up against the frigid cold, about 100 yards downwind from the Abraxas Mars research station in Antarctica, near Scott's Base, watching the southern lights, the aurora australis, playing across the frigid, darkening skies. The ethereal curtains of green and violet light shimmered and danced, a silent, celestial spectacle. I took a gulp from the bottle of whiskey safely cradled in the thick glove of my right hand, and then another, welcoming the slow, creeping numbness of gradual oblivion. My personal life was in tatters, a wreckage of my own making, and I had been thinking about death. Not my own, not suicide, but murder. The murder of my beautiful, brilliant wife. I had it all planned out in my head, a cold, perfect crime. Nobody would suspect a thing. I lifted the bottle, the amber liquid swirling within like a captured nebula, as if it held all the secrets of life and loss. She had betrayed me, yes, but only after I had betrayed her a dozen times over. I couldn't trust her, but the truth was, I couldn't divorce her either. She was my partner in every sense, half owner of Abraxas Thunderbird Space Corporation. She knew all my secrets, professional and personal. My beautiful, brainy babe had me by the balls. I took another long, burning guzzle of whiskey. Killing her would be easy. I had the training for it, from my time as a Navy SEAL. I had killed men with my bare hands, a fact I was not proud of, but a fact nonetheless. But in the quiet, desolate honesty of the Antarctic night, I knew it was all my fault. My drinking, my carousing with anything that looked good in a short skirt. Was it any surprise she had finally sought solace, and perhaps revenge elsewhere? She had apologized, begged for forgiveness. But my stupid male pride couldn't handle it. The truth, the one I kept trying to drown in whiskey, was that I still loved her. I needed her. She was my best friend. It's a strange and terrible thing, to love a woman so much and at the same time fantasize about pushing her in front of a train. I had come to Antarctica, to this desolate, Mars-like landscape, to sort things out, to think. And now, I was having second thoughts. It really was all my fault. I took another slug of whiskey, the burn soothingly and numbingly tracing its path all the way down. The auroras continued their silent, majestic dance, and that's when I saw it. A new light, different from the aurora. It was a spiraling hoop-like ring of coiled, white light, like a giant searchlight from the heavens, beaming down in a widening arc sweeping across the frozen tundra. It was coming closer, and then I was at the center of it, enveloped, looking up through a narrowing, black tunnel of swirling, circling lights. I blinked in stunned surprise. At the other end of the tunnel, like looking through the wrong end of a telescope, I saw myself. And then, like a bolt from the blue, I was lifted into the air and tossed like a rag doll onto the frozen ground. The world spun, the breath kicked out of me. I lay there, dazed, confused, as snowflakes began to drift lazily down from the black sky. I slowly sat up, checking to see if I was still in one piece. My whiskey bottle was gone. The wind was picking up, the temperature dropping. I needed a drink, badly. I stumbled to my feet and began to make my way back through the falling snow to the research station, Abraxas 1. I entered the station, the thick metal door clanging shut behind me. As I brushed the snow from my heavy coat, I sensed that something was wrong. The interior looked different. The furniture was rearranged. Several of my employees, people I had had dinner with just the night before, looked at me with surprise, as if I were a stranger. And the art on the walls had changed. Instead of the detailed panoramas of possible Mars landing sites, there were paintings of what looked like a giant, ugly hubcap floating in space. And the pictures from our rovers, the proof of Martian lichens and algae that was the foundation of our mission, were gone. Somebody been redecorating? I asked nobody in particular. I was met with blank, quizzical stares. I was still dizzy, still half drunk, so I let it go and headed for my room. The next morning, sober, the strangeness intensified. All my luggage, my gear, was missing. All I had was the watch on my wrist and the clothes on my back. My wallet contained a return plane ticket from Australia to the US. That was it. It was as if I had arrived with nothing. Where the fuck is my gear? I bellowed, but no one had an answer. I paced, shouting and grumbling, and then my eyes fell upon a digital clock on the wall, displaying the date. "What the hell is wrong with that clock?" I shouted, but there was nothing wrong with it. According to the clock, I had lost 2 weeks. I swore I had only been there for 2 days. My plane back home was scheduled to leave the next morning. My corporate helicopter was also missing from the helipad. I was fuming. I arranged a ride on another chopper to Williams Field, where my corporate jet should have been waiting. It wasn't there. A series of frantic phone calls revealed that my jet was sitting in a hangar in Melbourne, Australia. "But that's impossible!" I shouted into the phone. "How the hell could I get from Australia to Antarctica without a damn plane?" Somebody was fucking with me. I hitched a ride on a military transport to Melbourne and boarded a commercial flight for San Francisco. A little gray-haired old lady was sitting in my seat. The airline had no record of my ticket. They found me another seat. I ordered a whiskey and picked up an in-flight magazine. And then I got the next bolt from the blue, a picture of Barack Obama, with the caption, "President Obama." I turned to the man sitting next to me. "Is this a joke? When did Obama become president?" He looked at me as if I were a lunatic. "He was elected in 2008. "Right," I said. "But he's the vice president, not the president." My fellow passenger stared. "Biden is the vice president. Obama is the president." "What are you talking about?" I snapped, my patience gone. "Kennedy is president. Kennedy is dead," he said, edging away from me. "JFK was assassinated in 1964. I felt sick. "Dead? When did this happen?" "Kennedy died of old age in 2001. His son is president now." The man just laughed uneasily. "You're confused, buddy. Maybe you ought to lay off the booze. Both the Kennedy brothers were assassinated in the 1960s. Everybody knows that." He gathered his things and moved to another seat. I felt dizzy. The world was spinning. Had I lost my mind? I tried to activate my watch, to access the quantum library, but nothing happened. No holographic screen, no signal. The pilot and a stewardess came over. I explained about my watch, and I quickly realized from their questions that they had no concept of quantum computing. This world was still in the primitive age of the internet. I borrowed a laptop and went online. And there it was, in black and white, a different history. A parallel world. JFK and RFK both assassinated in the 60s. No sustained mission to Mars, just a giant money-sucking space station, that hubcap in the sky, built in part by my own company, Abraxas. And then, as we were landing in San Francisco, I found it. The obituary. My wife had died 1 week ago in a car accident. I was stunned. The bastard killed her, I thought. He had used my own plan, the perfect crime I had conceived and then abandoned. I had changed my mind because I loved her. This other me, this double, had gone through with it. I rented a car and drove to my house in the Los Altos Hills. I sat across the street, watching, waiting. The lights were on. The bastard was home. A red sports car pulled up. It was Jade, the daughter of one of my best friends, 18 and beautiful. I had always been fond of her, like a niece. Never touched her. The front door opened, and there he was, my double, holding a bottle of whiskey. He put his arm around Jade, pulled her inside, and closed the door. And in that moment, I decided. He was a murderer. He was defiling a young girl I cared about. He deserved to die. And killing him would solve all my problems. I could take his place. The next morning, I did it. As he stepped into his office, a quick, clean strike with an ice pick. That night, I burned the body in the industrial incinerator at the Abraxas labs. When I got home late that evening, I poured myself a drink. The doorbell rang. It was Jade, crying about a fight with her boyfriend. She threw her arms around me, sobbing. And as I held her, careful not to spill my whiskey, I looked out into the night, past her red sports car, and into the street. There, in the darkened shadows, was another car, and a man standing next to it, looking back at me. I gazed long and hard, a cold certainty creeping into my soul. I closed the heavy oak door. I know who he is. It's me. Another double from another universe, come to this world. How many more will show up, I don't know. But what I